So now that we know basic equations for capacitors, and I want to remind you because we're going to use them quite a bit, C equals Q over delta V, which I often prefer to write as Q equals CV. I just remember it better that way. And then the various U equations. My favorite one really is U equals 1/2 Q delta V. I don't know that really is delta U, but you can use any of them because remember, of course, it's 1/2 C delta V squared or Q squared over 2C because there's always a 1/2. But now we're going to link capacitors together because one capacitor, that stores some charge, and so it stores energy physically. And by the way, compare and contrast with a battery. A battery is a source of moving charges, but it's a chemical source. This is a physical storage. You just move them around. So now I'm going to put two capacitors in a series combination first. So remember, series means one after another. So I'm going to have a battery over here with some potential difference, and I'm going to connect it to the top plate of a capacitor. Wow, pretend that was betterly drawn. Betterly drawn? Oh my gosh. Okay, and then I'm going to hook up a second one. I'm kind of like attaching to the middle of the plate is what I'm trying to show there. And then the bottom plate of the second one. This was a lot better on my planning sheet. Okay, and I am going to double check the whole thing's on the screen. Really? Okay. So this is capacitor number 1. This is capacitor number 2. So when they are first connected to the battery, electrons from the battery leave the negative side. So here are electrons. They're negative. And they leave and they go fill up here. So let's just draw 4 of them doing that. Well, those 4 repel electrons from this one. So those 4 electrons leave. So because they leave, this plate is now missing 4 electrons. Well, there's 4 electrons can only go up here. They can't go any farther. There's this air gap. So unless we make air a conductor, which is lightning, dielectric breakdown, these electrons that left this plate can't go any farther than this. But then they will repel electrons from here, and then those electrons go back to the battery. And so this continues happening until the capacitors can't hold anymore. And the amount it holds depends on the capacitance and the voltage applied, as we talked about before. So first of all, we're hardly ever going to draw it this way. A capacitor in a circuit looks almost like a battery. So a battery has a long end and a short end because this is the positive side of the battery, this is the negative side of the battery. A capacitor is drawn as 2 parallel lines. So this is the potential difference of the battery, this is capacitor 1, this is capacitor 2. So they're almost the same, so you have to be a little careful that you make sure you draw these unequal in length in the correct direction and these equal in length. So the first thing I want you to notice is because we had these electrons, however many come off here, repel that same number, because these two charges are always equal and opposite, and those can only go here. So the total charge stored on plate 1 is equal to the total charge stored, or see, on capacitor 1 is equal to the charge stored on capacitor 2. And that is the total charge stored by this battery. If we say 4 electrons left here, 4 electrons eventually came back. So the Q total is equal to the charge on each one. Now I want to remind you with resistors, this is a long time ago I know, but with resistors the current was the same everywhere because the current kept flowing. If you have a series combination, the current went through the first one and then the second one and then back to the battery. For the same reason, because current is the movement of charges. So whatever charge comes here repels the same number of electrons, which get stuck here, which repel these. I can't believe I drew those as negative signs. Bad teacher, bad teacher. Those are positives because the electrons left. Oh my goodness. Well, if I use this as a thumbnail, it'll be after that's fixed. Now let's talk about potential difference. I want you to recall that, I need to box this. I want you to recall that a conductor is an equipotential. So let's say this potential difference is 10 volts. That means the top is at 10, the bottom is 0, or any other combination that subtracts to give you 10. But let's just say 10 and 0. Well, that means everything along this wire, including this plate, is at 0 volts. This is at the same potential, everything inside this box. And I deliberately went through the middle of the battery there. Also, so if this is all at 0 volts, let's say, well, the top side of the battery is connected by a wire to the top plate. So all of this is at the higher voltage, just 10 volts in my example. So let me get black. The middle part is also connected by a wire. So it's at some value between 10 and 0. Now it could be 5, but it's only going to be 5 if these two are equal capacitances. So let's just make one up and say maybe it's 6 volts. So the potential difference across C1, which would be 10 minus 6 is 4, and the potential difference across C2, which would be 6 minus 0, which is 6, always is going to add up to the total potential difference of the battery, always. So if I made up any number here, because it would have to be between 10 and 0, no matter what it is, then this difference, 10 and whatever, and this difference, whatever and 0, would always add it back to 10. So we summarize that by saying V for the battery is equal to the potential difference across capacitor 1 plus the potential difference across capacitor 2. We did this with resistors also in series, but we didn't do a lot with it. We're going to do more this year. Now we need a rule to combine the capacitors. If we have two capacitors in a circuit, we usually want to know what's the equivalent capacitance. So put these two together. What do you get? I'm actually going to show you the derivation. We're going to start from this equation. Delta V battery equals delta V1 plus delta V2. And then if we rearrange the definition of capacitance, delta V is equal to Q divided by C. So instead of the potential difference across the battery, I'm going to use the total charge divided by the equivalent capacitance. Instead of the voltage across capacitor 1, it's going to be the charge on capacitor 1 divided by the capacitance capacitor 1. And the same for 2. Well, we also already know that all of these charges are equal. So we can divide by whatever that number is, and it cancels out everywhere. So we're left with 1 over equivalent capacitance, make sure it's on the screen, equals 1 over C1 plus 1 over C2. We had this same kind of rule with resistors, except this was the rule for parallel resistors, this 1 over rule. It's the rule for series capacitors. And it's because potential capacitance was defined as charge divided by potential difference. As I'll remind you in the next unit, resistance is defined as potential difference divided by current produced. So remember, current is the flow of charge. So these two definitions are upside down compared to each other. And so capacitance and resistance are kind of inverses-ish, though they're unrelated things. Well, they're related, but not directly. But that flips the rules. So now we're going to do the same thing for a parallel circuit. So parallel, again, we have a battery, and we have these. I'm going to try to do a better job this time. We have capacitor 1, and we have capacitor 2, drawn as a regular circuit. C1, C2, delta V. So now, electrons leave the battery. Dum, 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 dum. Oh, I have a choice. Some of the electrons are going this way. Some of them are going to go over here. And depending on what these capacitances do, one of these can handle more than the other. So I'm going to draw 4 here and 6 here. Well, that repels an equal number of electrons here, which go back to the battery, and an equal number of electrons repelled from this one, which go back to the battery, and they join together, the two sets of electrons, to go back to the positive side of the battery. So the charge stored in the circuit is now equal to the sum of these charges, because the total amount of charges that moved, some went on Q1, some went on Q2. Now for potential differences, remember, every place that's a conductor is at the same potential. So the top side of the battery is connected to this top plate and this top plate. So everything here is at the higher potential. And then the negative side of the battery is connected to this bottom plate and this bottom plate, so all these are at the same potential. So if this is 10 and 0 again, this is 10 volts, this is 10 volts, and this is 10 volts. The potential difference across the battery is equal to the potential difference across number 1, which is equal to the potential difference across number 2. Again, just like with parallel resistors, when they were in parallel, it was the same potential. So now we want to do the same thing with find the equivalent capacitance. So we again start from our summation rule. Q total equals Q1 plus Q2. And remembering that Q equals CV, delta V. So Q total would be C equivalent times the potential of the battery. Q1 would be C1 times potential across it. And Q2 would be its capacitance times its potential. But all of these potentials are the same, so they cancel out. And we're left with C equivalent equals C1 plus C2. So if we box those three rules, so now I'm going to summarize. I'm going to do a compare and contrast. Series, parallel. Series, same current. See, I did it for resistors. Same charge. Parallel, same potential difference. For series, the potential differences, I was forgetting something, have to add up. For parallel, the charges have to add up. And then because of that, in series, we have the reciprocal rule. And in parallel, we have the just straight summation rule. So don't get them backwards, because these two are the same basic ideas as resistors were, but these two switched which kinds. So be careful. I'm going to stop this video now, and then I'm going to publish a second video where I do a full solving of a combination circuit. You will have in the first assignment over this a straight series and then a straight parallel, solve everything. And then I'm also going to give you some combinations where I only want you to find the overall equivalent capacitance, where you'll do the series and parallel in turn. So you may want to watch the first half of the next video before next time, or you may want to watch the whole thing, or you wait and see how much you remember.